start. All right, let's go. Okay, so today's lecture is going to be on neutrinos and specifically something called the solar neutrino problem. We've talked about neutrinos before, but not in much detail. So let's start out with what neutrinos are. So in the early 20th century, I think it was Wolfgang Pauli, he proposed the idea of a neutrino because they were studying something called beta decay, which is where a neutron decays into an electron and a proton. The problem that they faced though was that if it was just an electron or proton, then it wouldn't conserve the spin, momentum, and energy of the reaction. So Wolfgang Pauli, I believe it was, proposed another particle that he originally called a neutron, but the other neutron that we know today was also just discovered and called a neutron, and so he called it, or it wasn't Pauli, it was Fermi who called it a neutrino, because this one was like a smaller version. It's a little neutral particle. So that's where neutrinos were first kind of postulated from. They're tiny, almost massless. They're originally predicted to be massless, but we'll see that that's not the case actually. And they didn't have any charge. So yeah, extremely light, and they rarely interact with other matter because we talked about the four forces. So electromagnetism, gravity, strong nuclear force, and weak nuclear force. Neutrinos only interact through the weak nuclear force. And so that means when they pass through matter, they interact very rarely. And there's three kinds of neutrinos, electron, muon, and tau neutrinos, and that corresponds to the three types of leptons, electrons, muons, and taus. Okay, so that's just kind of a recap on neutrinos. Okay, so the important part is that neutrinos are produced in the process of fusion. So in the sun, when atoms are fused together, when hydrogen atoms are fused together to form helium, it produces a neutrino. You can see the Feynman diagram here if you like the technical part. But essentially, the important part is that it's kind of beta decay but backwards, where instead of a neutron decaying into a proton turns into a neutron and releases an anti-electron or a positron and a neutrino. And so this is happening in the sun all the time, and so because the sun is so massive, so much matter is being fused that tons of neutrinos are being produced. I think it's about 10 billion neutrinos are passing per second in an area the size of a stamp. So neutrinos are passing through us at all times, and they rarely interact with matter. But they're being produced by the sun. So let's say we want to measure neutrinos, because maybe we have some theories about how fusion in the sun works, and we'd like to confirm those theories to make sure that's how the sun actually works. So how do you measure a particle that pretty much almost never interacts with matter? You have to use a lot of matter. And so this is where the home-stake experiment comes in. So home-stake experiment started in 1970. What it was is that in the home-stake mine, a couple kilometers underground, they took a 100,000 gallon tank and filled it with perchloroethylene, which is like dry cleaning fluid. And so the reason why is because perchloroethylene has a lot of chlorine atoms. And so that's where the important part of the fluid comes in. So chlorine, when a neutrino interacts with one of the protons in chlorine, with one of the neutrons in chlorine, occasionally it'll undergo kind of beta decay but reverse again, where you have a neutron that comes in and combines, a neutrino that comes in and combines with a neutron, and that forms a proton. So what happens is that one of the neutrons of the chlorine atom interacts with the neutrino coming from the sun, turns it into a proton, and so the chlorine atom turns into an argon atom, radioactive atom of argon. And so this would happen, there would be quadrillions of neutrinos passing through the detector like every second, and neutrinos interact so rarely that you'd only get about one a day. So out of the quadrillions of neutrinos, you only get one interaction a day that turns into an argon atom. And then after a while, the leaders of the experiment kind of just bubbled up the argon atoms out of the chlorine, and they had like tens of atoms after weeks of the experiment going on. So that's the home-stake experiment that was designed to kind of detect neutrinos coming from the sun and determine how many were coming. So there was a problem though. They ran the experiment for a while, and then they compared the measurements with theoretical predictions, and it turned out that they only measured about a third as many neutrinos as being predicted. And then other neutrino observatories confirmed the results that only about a third the expectation of neutrinos were being measured. So that's a problem. So there's a couple of possibilities for what's going on. So first of all, you could have the sun is going out. That would be a big problem. So for some reason, maybe the rate of fusion in the sun has decreased massively. Second possibility, nuclear physics is wrong, and that there's some other kind of mechanism that's suppressing the creation of neutrinos, and so we'd have to redo nuclear physics. Or there's a third possibility of something called neutrino oscillation. And that's the idea that the neutrinos kind of change flavors into each other. Because the neutrinos that are created in the sun are all electron neutrinos, so maybe those are changing into the other two types of neutrinos as well. And so then we had a couple of other experiments. We have Super Kamiokande and the Sudbury Neutrino Observatory, which was that picture that we saw in the first slide. So Super Kamiokande, that actually provided some earlier evidence for neutrino oscillation, except it wasn't measuring neutrinos coming from the sun, it was measuring neutrinos coming from the upper atmosphere. That actually has to do with my senior project, is analyzing the data from Super K. But that kind of provided some early idea that maybe neutrino oscillation was the right answer. And so then came the Sudbury Neutrino Observatory. And so the difference between SNO and all of the other experiments is that it could actually tell what kind of neutrino it was, or it could tell how many neutrinos were coming in, and it could also tell how many of them were electron neutrinos. And so when they actually performed the experiment, they found that the correct number of neutrinos that they predicted were coming in, but only a third of them were electron neutrinos. So the other experiments, the homestake experiment, was only measuring the electron neutrinos. So sun's not going out, that's a good thing, and nuclear physics is broken, also a good thing. But now we know that neutrinos are oscillating between the states. So that has some interesting implications that we hadn't really thought of as being true before. So the implication of the neutrinos oscillating is that neutrinos actually have mass. Previous to this, it was believed that neutrinos were massless particles, and if they did have mass, it would be extremely light, but they were assumed to be massless. But if they're oscillating, that means they must have mass. And the reason for this is in special relativity, actually. So if we go all the way back and remember from special relativity that an object that's moving near the speed of light experiences time slower. And as you approach the speed of light, time goes slower and slower and slower. So for an object that's traveling at the speed of light, time is actually frozen. So for a photon traveling through the universe at the speed of light, it wouldn't experience the passage of time. So if neutrinos are massless, that means they're traveling at the speed of light, and so they wouldn't experience the passage of time. The problem with that, if they oscillate, an oscillation is changing between states over a period of time. So if they're oscillating between states, that means they have to experience time. And so therefore, they have to have mass. They can't be traveling at the speed of light because they're oscillating. So because they're oscillating, they experience time, and therefore they have mass. So they're not traveling at the speed of light. Okay, so neutrinos oscillate. They oscillate between the flavors, and they have mass. So now all we have to do is just match what flavor of neutrino has what mass, right? That seems simple? No. That would be way too easy. Nature is way more complicated than that. So before we get back into that, we have to go over some background quantum mechanics, and this is a little bit deeper than what we were going over before. So, do you guys remember what a wave function is? We talked about that last year and then kind of this year as well. So wave function, it's a function that describes the state of a system. And if you square the wave function, you get a probability wave, and so probabilities of measuring the system to be in a certain state. So, but the important part is, it's a function that describes the state of a system. Here's a new term that we haven't covered before, an eigenstate. So an eigenstate is a possible wave function of a system where the quantity that you're measuring is in a definite state. So there's no probability of measuring it one way and probability of measuring it another. If it's in an eigenstate, then it has 100% chance of being that state. So for example, if it's in a position eigenstate, then with a certain position associated with it, then every time you measure it, it's going to have that position. So a wave function can be in an eigenstate where it has a definite position or a definite some kind of measurable. And it also can be in a superposition of eigenstates. So we talked about superpositions before where a system is kind of in a state of this and that, or like half up and half down. So what a superposition is that the wave function is actually a couple or many different eigenstates kind of added together. And so here's an example. So let's talk about, we talked about Schrodinger's cat, and it's kind of a classic example. You can ignore the brackets. That's called bracket notation. It's just kind of the standard notation of a wave function. So you have two eigenstates. You have dead and alive for the cat when it's in the box and nobody's measured it. So it could be in the dead eigenstate after you measure it, or the alive eigenstate after you measure it. But before you measure it, it's in a superposition of the two eigenstates. And so that's represented if each eigenstate has an equal probability of being measured. It would be 1 over rad2 dead plus 1 over rad2 alive. And so that corresponds to, if you square the wave function, that means it's half dead and half alive. So it has 1/2 probability of being measured to be dead and 1/2 probability of being measured to be alive. So that's kind of a simple example of an eigenstate. And so that's the important part, is that a wave function can be a linear superposition, or just superposition of eigenstates. So a couple of possibilities added together. So let's take this back to neutrinos. Don't try and write down these equations. Please don't, for your own sanity. I'm just going to, just kind of there for example. So when a neutrino has a definite flavor, like say it's exactly an electron neutrino, so it's in the electron neutrino eigenstate. When it's in that state, it doesn't have a definite mass. So when it's in that state, in the terms of mass, it's actually a superposition of different mass eigenstates, 3 to be specific. And so that's what this equation is. There's a point. That's what this equation is. You can kind of ignore the u part. That's kind of the coefficient of the eigenstates before, like how it was 1 over rad2. That has to do with the actual probability of measuring it. But the sum, we know that the sum is when you have multiple things and you sum them, you add them together. So that means if this is the eigenstate of a definite position, then these are eigenstates of definite momentum, and so you have multiple eigenstates of momentum added together. And then the same with the second equation is that you can do it the other way around. So it has a different, sorry, did I say momentum? I meant mass. So when it has a definite mass, when it's in a mass eigenstate, the wave function can be expressed as a superposition of flavor eigenstates. So if it has a certain mass, it's like partially electron, partially muon, and partially tau. And so as the neutrino leaves the sun and it travels through space, it oscillates through both these flavor eigenstates and mass eigenstates. And so that's what this equation kind of is. So you can see that the probability of measuring of a certain a neutrino starting out a certain way and measuring it to be another flavor. So let's say it starts out as electron and you measure it as tau later. It depends on how long it travels, which is L, and the energy of the neutrino, which is E. And the rest of that you can just kind of ignore. It's a bunch of constants. And it's also a sine function. So it oscillates through these different flavors and masses as it travels through space. And the rate of oscillation depends on the energy of the neutrino and how far it travels. So that's where the kind of solution to the problem comes in, is that these neutrinos are in superposition. So when it's created in the sun, it has a definite flavor, electron, because the fusion only generates electron neutrinos. And then as it's traveling through space, it oscillates between the 3 different mass eigenstates and 3 flavor eigenstates. And when it has a single mass, it doesn't have a single flavor, and when it has a single flavor, it doesn't have a single mass. So it starts out with a single flavor. After a while, it's oscillating. It could be a superposition of the 3 mass eigenstates that has maybe an equal probability of being measured of either. Sometimes it's entirely one mass, sometimes it's entirely one flavor, and sometimes it's just somewhere in between, where it doesn't have either a definite flavor or a definite mass. And so the neutrinos, as they travel through space towards the Earth, they're oscillating, and so that's why when they measured only a third of the neutrinos to be electron neutrinos, as they were expecting, it turns out that the neutrinos were oscillating into the other states. And so that's kind of the whole summary of what we discovered, is that neutrinos are really weird because their masses and their flavors don't match up. Sometimes they're one mass and a bunch of different flavors, sometimes they're one flavor and a bunch of different masses, sometimes they're just in between. And that's really unique among fundamental particles. Like quarks don't do that, electrons don't do that, only neutrinos. And that's kind of why particle physicists really like neutrinos, because they're really weird. And that's really what the moral of the story is that neutrinos are really weird particles and they do some crazy stuff. All right, thank you, that's the lecture. Any questions? No? Okay. Yeah?
What's the difference between nuclear fusion and fission? I always forget.
Okay, so fission is when you have a heavy nuclei and you shoot a neutron at it and it splits into two less heavy nuclei and gives off some radiation. Fusion is when you have two light nuclei, like two hydrogen atoms, and you fuse them together to form a heavy nucleus. Okay? Alright, so I don't really have anything planned for the next 8 minutes. We could talk about what we want to do for the club for the rest of the year. Or I mentioned how the Super Kamiokande experiment has to do with my senior project. I could go over that really quick. Do you want me to? Senior project? Okay. Let me pull up some... actually, you know what? Okay. I'll just talk about what my senior project is really quick. So, I talked about solar neutrinos here. My senior project has to do with atmospheric neutrinos. That's generated through a different process, but it's when cosmic rays strike the atmosphere. They generate specifically muon neutrinos. And so there's this other detector called the Super Kamiokande, which is different from the SNO detector. It's more of like a giant cylinder, and it's buried like a couple of kilometers underneath Japan. And so it could measure the atmospheric neutrinos that pass through the detector. And so what it found was that when you have, and it could also tell what direction they're coming from. So because neutrinos interact so weakly, they can pass through the entire Earth, and you could still measure them on the other side of the Earth. So what they found was that, if I just hit camera, will it go to the... Yes. All right. So what they found was that the neutrinos that come from straight down, they were pretty much roughly the exact amount they expected without neutrino oscillations. But when they measured the neutrinos coming from like the other side of the Earth, the length that they traveled actually changed how many of them they measured. So that's this graph right here. So here, this is what this is. So this axis is... Oh. Okay, so this axis is the cosine of the zenith angle. So really what this means is that neutrinos over here are coming from straight up, neutrinos over here are coming from like the side, and neutrinos over here are coming from straight down up through the Earth. And so because it's a cylinder, that means it has a larger surface area on the side, so that's why you would expect more coming from the side, and that's why there's this bump here. But essentially, the blue dotted line is the expectation without oscillations. And the red, or actually the black like bars, that's what they actually measured. So neutrinos coming from straight down were pretty much exactly what they expected. Neutrinos coming from all the way in the bottom of the Earth were not what they expected at all. There were way fewer. And so the problem was figuring out a couple of constants when it comes to neutrino oscillations. So let me write an equation. So there's an equation that... oops. So when we're talking about this case of neutrino oscillations, remember this equation right here, this massive one. This is when you have 3 flavors. In this special case, you can really only talk about 2 flavors of neutrinos, the muons and tauons, because I won't get into why, it's really complicated, but really don't have to worry about mu and tau. And so that gives a simpler equation, and that's, so the probability of measuring a muon neutrino turning into a tauon neutrino is sine squared 2 theta 2 3 sine squared delta n squared 4e. I think I'm missing a couple constants in there, but it doesn't matter. So in particle physics, you can just call like h0 and g, or 1, whatever. So it depends on a couple of constants. So first, you have the length that the neutrino travels and the energy it has when it is generated. And then there's these two things, theta 23 and delta m squared. These are two constants that have to be determined experimentally. We don't really have a way to predict them. And so that's kind of what my senior project is figuring out the values for theta 23 and delta m squared by taking this data, this data of how many neutrinos it measured as a ratio of how many it expected, and then I think I have the other paper here. Yeah. This is the flux of how many, it's essentially how much energy the neutrinos have and how many of that certain energy. And so that's right here. And so essentially what I'm doing is finding for each of these lengths, so each of these kind of like sections corresponds to a different length because the neutrinos are created like about the same height above the atmosphere. And so this would be like 20 kilometers because it's coming from straight above. Over here would be like the diameter of the Earth. And so each of these corresponds to a different length. And so for each length, I have to find, essentially I'm writing a computer program to come up with a random value of this and this out of, come up with a random value, plug it in to find an average probability that you would expect with neutrino oscillations for each of these lengths, and then using something called a chi-square, which is from statistics, that kind of tells you how well your prediction fits the observations. And so the computer program is going to test thousands and thousands of possible combinations of theta 23 and delta m squared, and then figure out which one is best by finding which one has the smallest chi-square. And so that's really what the project is finding the pair of those two values with the smallest chi-square that best fits experimental data. Yeah?
So behind the delta m squared, is that an L?
That's an L for the length that the neutrino travels.
Alright, and underneath that's a 4.
4e. And E is the energy of the neutrino. So some neutrinos have a lot of energy, and that would be the ones over on this side. And some have a little bit of energy. And so you kind of have to find an average energy that you have to work with. And so I won't get into how I'm finding the average probability. It has like integrals and cross-section. Anyways, that's what my senior project is, that it has to do with atmospheric neutrino oscillations and figuring out the fundamental constants for theta 23 and delta m squared. And that's atmospheric neutrino oscillations as opposed to the solar we were talking about. Okay, I don't really have anything else to say, so, all right, good lecture.
When's the diffusion chamber going to be?
Oh, diffusion cloud chamber. We should set up a fundraiser to pay for more stuff. Definitely not going to abandon it though. Maybe next time, depending on whether we can get some money by then. The next time we're meeting, the next even Friday isn't until December 8th, and that's going to be the last meeting of the semester. Maybe we can have an extra meeting or something, I don't know. But, so yeah, next time, maybe we'll do the diffusion cloud chamber. I'd also like to get that day where we have a discussion of different thought experiments going. Actually, I'll show you the website. Okay, this is weird. Never mind. Just on the club website, physics.weebly.com, there is a Google form that has a place for you to input your thought experiment. Just write it. So if you have any ideas. So go on the website and write your thought experiment there. All right. Thank you guys very much. Good meeting. See you guys next time.
All right.